Do you want to? You're going to be coming back through there a lot? If that's yeah, we just found a little bug. Only if you're, I think only if you're on, only if you don't have a package called Theano installed. So, and it comes with Anaconda for Linux if you have that. So that's why we're all in Linux boxes and didn't pick this. I don't think so. Yeah, I just checked their thing. So likely if you have Mac or basically probably everybody should install the patch is the likelihood. Yes, you can. Yeah, you could pip and like do -e and give it the git URL or something if you want. Okay, we're gonna go ahead and get started. It's 9 o'clock. My name's Jason Moore. Hey, Tarun, just a little quieter. I'm gonna get started. Well, welcome. Thanks for coming to the tutorial. We're gonna be talking about doing simulation of multibody dynamics using Python. And we're going to use several packages in the sort of scientific Python ecosphere and domain. My name is Jason Moore, and I'm a postdoc at Cleveland State University in Ohio, and I think about how objects move a lot and work on multibody dynamics. I work in a walking lab right now, so we study how people walk and move, how they balance, what their control is. And I have with me Obina Nawana. He's a grad student in our lab at Cleveland State, and he's going to be teaching some of the notebooks and assisting. And then Tarun Gaba, he is a undergraduate student from IIT Varanasi, and he worked with us on a Google Summer of Code last year and helped create some of the tools that you guys are going to use today. So I guess, yeah, the first question is, does anybody not have the software installed? You don't have the software installed? Okay. You want to help him, Bina, get going there? And this, you have one of these ready, Tarun? And so the other note that some of you have already heard is that we just found a small bug due to an import error. So you're going to need to update this package, PyDecodegen. And the easy way to do that is just come to this web page, download that zip file, and unpack it. And inside of a command prompt for your Anaconda in this installation, if that's what you're using, you can type Python setup.py install, and it'll update this. So or ask Obina and Tarun, and we have some USB sticks with the patch on it too. Is that?
You need
IPython notebook. Yes.
This command in this directory?
Correct. Did you install Anaconda? Should come with all of that. If not, you're going to have to install. Yeah. Correct. Can you help him with that? He's having trouble with the IPython notebook. Oh, it worked?
Yes, but now it doesn't work anymore.
Okay, well, Tarun will give you a hand there. Anybody else with installation issues? Raise your hand so that these guys know. Okay. So to start off, I sort of want to get like a 10-second intro or so from each of you all. If you could tell me your name, where you're from, what your familiarity is with Python, the SciPy stuff, and then also dynamics. And then finally, what are your interests? Why are you interested in being here? Why is this tutorial interesting to you? And yeah, just keep it short so we can get through each person. You want to go? Okay. Great. Yeah.
Everyone, I'm Ivan. I'm an educator, or I write math physics books, and I want to create simulations to better teach math concepts because computers can do that very efficiently. So I'm interested in JavaScript, but Python seems to have good simulation. Well, Python is even better than JavaScript.
You got to say that at this conference, right? Cool. Great. You want to go? Cool. Thank you.
Good morning, everybody. I'm doing my master's in mechanics now. I'm doing controls. I know C, C++, MATLAB, but this is like my second day in Python.
Oh, good. Well, welcome to the world. Yeah.
My name is Andy. Actually, I'm not a programmer, but I have a physics background, so I'm still interested in this kind of stuff, kind of a hobby.
Cool.
I'm Nick. I'm from LA. I'm a web developer. Been using Python for a long time now, and this is kind of outside my professional area. But I try to take classes that are just over my head to make sure that I'm rounding out those edges. And I have like a hobbyist interest in some
Cool.
robotics. So.
Fantastic. You guys in the back? Okay. Cool.
My name is Ken. I went to Survey Motion. I know Python pretty well. I the SciPy dynamics stuff, so check it out.
Good. Great.
My name is Steve. I work for John Deere in their GPS operation division in LA. And I'm not doing anything with Python now, but I have a physics and math background, obviously.
Cool. Fantastic.
My name is Adam. I'm from Chicago, and I've been working on Python for about 3 or 4 years now. And I just had an interest in hardware for robotics. As a hobby, and kind of working on another project that
Great. And how many people made it through like calculus and stuff in college? Is that pretty much everybody? And like differential equations, you know what that is? Yeah, and then vectors, right? Pretty much. Okay. Okay. So we'll hit on some math concepts that might bring you back to those horrid days of calculus class, but that's how we're going to make these things work today. Okay, I guess also too, if you want to pair up with the person beside you and help each other along, that's fine. Or work alone. In either situation is fine. Okay, well, to start up here, you want to open a command prompt, and you want to be in this notebooks folder that has all that IPython files in it from the tutorial download. And you should just be able to type IPython notebook, and your web browser is going to open up this view of all the notebooks that are in that browser. In that directory. And we're going to go through them one by one. There's 10 of them, and we may or may not. We'll see how fast we go through, but sometimes we have to rush that last one. And the first one's going to be relatively short because I think most people in here sounds like they know Python. I've given it to other folks that haven't seen it before. I know we got one fellow that it'll be new to. So Obina's going to lead us off on the this intro notebook. And if you have any questions, right, just raise your hand.
All right. Hi, everyone. Like you said, my name is Obina. I'm going to start off here with just a brief intro on the IPython notebook. Are you all familiar with the notebook itself? Have you? Okay, well, the IPython notebook is just a browser-based way to interact with your code and display the media in the same environment. How it's organized is we have individual cells that you can run code in, or either input text in. Here we see text cells with information for you. And further down, there are code cells. To evaluate a code cell, you can hit Shift-Enter or Control-Enter. Shift-Enter will evaluate the cell and go on to the next. Control-Enter will evaluate the cell and remain in that cell. So the front end here is the browser, and the back end we have the kernel actually executing the code. If there's ever an issue where the kernel freezes up and you need to restart or clear all your environment variables, you can go up here, kernel, interrupt, or restart, and you can just start fresh again. Along here, various toolbars, buttons to insert a new cell, or you can run all the code in the cell. File open, and pretty self-explanatory up there. So let's continue on. Here we have the magic commands. These are commands that control the notebook itself. This first command line magic is ls magic. It lists all the commands available for you. So you hit Shift-Enter. So that's quite a deep list. We won't be using all of them. The main one we'll be using is the load magic, where you can load. You run the cell. It'll load code that you have saved somewhere else on your computer. For example, here we have this utils.py file that will load up, and then you can run that cell. If you ever get stuck, these 4 commands will help you kind of find some help. Question mark will give you a quick overview of IPython and all its features. If you use the magic command quick reference, you'll get a reference for the IPython notebook. If you use that question mark after a command, you can get information on that command itself. And actually, if you use 2 question marks, you get more in-depth information. Okay, it usually would show the actual code for the function, but with the directory command, you'll list all the functions available in your workspace. So right now, they're only the default built-in commands because we haven't loaded any modules yet. And then we have the whois command. We'll load all your variables that are in your workspace. I'm going to just breeze through this next section. I assume you all know Python at least a little bit. So basic data types, data structures. We'll be using lists, tuples, dictionaries. And then functions. I'm sure you all understand this. So to import a module, we'll be using this command from the module. We'll import the functions as necessary. So here we have from NumPy, importing the array function. And here we have from SymPy physics mechanics, importing these functions. We'll be using those later. And then once you do that, those functions are available to you within the notebook. Now, specifically the SciPy stack, that's comprised of the IPython notebook we're currently looking at, and then these modules among some others. We have NumPy to manipulate arrays, matplotlib for plotting functions, plotting functions, SciPy for general scientific functions, so filters and whatnot, and then SymPy for symbolic computations. So let's get into NumPy. You run this cell numpy import random, and linear space 0 is an array range. These are just a sample of functions to manipulate arrays. As you can see, creating arrays is kind of like creating a list of objects. You can create an array from a list. You can create a random array of 5 elements. Linear space creates an array from 0 to 10 with a certain number of elements, or 0 to any other number, and with a certain number of elements here, 5 elements. And a range will give you a range from 0 to 14 going by 3 or whatever other number you want. But the default is by 1. You can access an array the same way you access elements of a list. So here we have a 3 by 5 array. We can access the 0th and the 3rd element, or the 2nd element here. And the mathematical operations on our list are element-wise, not if you're from the MATLAB world, it's array-wise. It's by array, but so each element here is added for example here, each element is squared and then added to itself. Okay, next we have matplotlib. This matplotlib inline magic function allows for your plots to display within the IPython notebook instead of externally. Here, import plotting functions, so we have the plots, subplots, and then different utilities to label your plots. And then additionally, we'll import some NumPy functions. Here we have a simple example of plotting some sine waves. We have our x-axis and then the 2 functions. And here we can plot 2 functions in the same plot, and then a 3rd function. These are the line specifications, so we can plot a dashed line, a blue dashed line here, a green circles here. Then we have the x label, y label, and legends. We have a list here with a list of all the legend items and the location of the legend. Similarly, another example, but a subplot. The plots are generated in this for loop, and this tight layout is, I guess, for aesthetic purposes, so the x and y labels don't overlap. So here, we'll get a little exercise for you to kind of get your feet wet, a little refresher here. What I want you to do is take this function here. It asks for 4 inputs, a time signal, and then amplitudes for 3 different sine waves, and it'll output 3 sine waves. And I want you to take that and plot it like this here. Okay? So all the code should be available in the previous cells for you, and then enter it here. And we'll be walking around to kind of assist you. So just walk around and see if anyone gotten pretty far in this problem, so we'll just load the solution here in the next cell. So see here, I used the A range to create a time vector from 0 to 5 going by every 10th of a second, then frequencies of 1, 2, 3. And then there's a function signature. And I plotted everything with the same, in the same line here. Oh, hold on. Gotta run this. All right. So next we have the SciPy module. From that, we're going to be using the ODE-NT. So it's integrated for ordinary differential equations. So here's an example. We just have the equation. We have the equation, our differential equation x. Our differential equation x, I'm going to integrate it to get x squared. And using this function ODE-NT, we have a differential equation dy, and our initial condition, our starting point, y naught, we're going to use that as 0. And we're going to integrate it at these points x. So from -5 to 5, I'm going to have 1,000 points between those. And it does our integration for us. Okay. Here's another example of a more complicated function. So we'll be using this later to derive our equations of motions. And then finally, we have SymPy. We're doing our symbolic calculations with this module. What this allows us to do is symbolically manipulate variables, and then afterwards, we'll take these symbolic variables and turn them into numeric equations so we can actually calculate the solutions here. So for example, we have these symbolic variables A, B, or we can even name them gravity or mass, spring constant, time, and they will be displayed as these letters, G, M, K, or T. And then here we can manipulate them algebraically. So we have a squared plus b over pi, just an example here. You can even have SymPy simplify that for us. So we have this kind of complicated displayed equation. We have it simplified to 12 times a to the 3rd power times b. You can even take derivatives for us. So we have gravity times time squared over 2. Take the derivative, or the indefinite integral, or even definite integrals. Okay, so that was a quick, brief run through just to get you guys started, but now we'll have Jason here who will give a more thorough introduction into kinematics and dynamics.
What is
D-
dy? For differential equation,
It's the equation you want to find the integral of. So in this example, the equation is just a line y equals x.
okay, y equals x.
Y equals x, yes. So the derivative's y squared, x squared.
The next notebook that we are going to go to is this dynamics overview. It's not really a lot of coding in this one, but I'm going to try to give you a crash course in dynamics. And this is probably beyond what you'd get in it is beyond what you'd get in a Dynamics 101 course, or maybe standard physics too. But these are sort of the concepts that it's gonna give you an intro to the concepts that we're gonna need to sort of build this problem up. So if you're wondering like what kind of things can I think about, with dynamics, we are typically talking about the motion of objects in the macro world, right? Everything that's governed by Newton's 3 laws of motion. And I work in biomechanics now, so we think about things like musculoskeletal models of people's bodies or animals' bodies, modeling how people might jump. I've also done vehicle dynamics and things too, so these are a couple examples, like a model of a bicycle or a motorcycle, a model of a quadcopter. So these are the kind of things that we can sort of build the equations of motion of, and then try to predict the motion of the object given the mathematical equations. So, like I said, the main piece of the puzzle here is Newton's second law, and the simplest form that we always see since high school physics is F equals ma. All the forces that are acting on some system are proportional to the accelerations that system is exhibiting. And you see that F is in general a vector, and A is in general a vector. So we're going to be working in vector spaces. And then the M term, the mass or the inertial terms, are the proportionality constants that relate the forces and the accelerations of some system. So this equation is, if we're interested in the position, how do we get position from acceleration? Any thoughts? Position from acceleration. Integrate. How many times? Twice, right? So Newton gives us a second order differential equation. If we replace A with dx squared dt, this is how the position x changes in time. You differentiate that twice, you can get A. But we're only able to figure out this equation fundamentally, but we're interested in x, right? Where is the thing in space after some time? What orientation it's in, its position, and to get that, we have to integrate those equations. And what Obina just showed you in the last slide was integrating a differential equation. And so we're going to eventually come back to that near the end after we sort of build up the equations of motion of the system, right? So vectors, I'm going to give a brief reminder, right? Vectors have magnitude and direction. That's what defines a vector, a length, and it points some direction. We also are going to think about vectors. We're going to think about vectors in 3D space, and when we're thinking on this flat plane, like vectors that point out of the board. If you see an arrow like that, the vector's pointing out this way, and then that's into the page, right? Unit vectors are simply the vector divided by its magnitude, so it gives you a vector of length 1 in the same direction. We can add vectors, right? A plus B, if I stack them together, I can get the vector A plus B. And that just amounts to adding their components. And here, I've got a little bit of Python code that we're going to use the SymPy vector framework here to add a couple of vectors. So the first thing is I'm going to have to create a reference frame, and I'll tell you what that is in a second, to do this vector work in. And then I can define a vector where I give it, I say that A is made up of components. The unit vectors are the n.x, n.y, and n.z, right? So these are the unit vectors in that reference frame, and I can give them some coefficient, and that gives me a vector A. And if I execute that, this is what sort of a vector looks like in SymPy, right? So it has the unit vectors in the three orthogonal directions of the reference frame or the coordinate system, and then you can do operations on them, right? And it adds everything correctly. So to add a vector, if you remember from vector, right, it just adds the components. Simple as that. Vectors can be scaled, and right here's I can multiply by a constant. That shows that. There's also dot products, right? Dot products are useful because they can tell you a few things. They can tell you the angle between vectors, right? So if you have two vectors and you take their dot product, it's equivalent to the magnitude of the two vectors times the cosine of the angle between the two. So that's useful. We can also get the vector's magnitude and do projections. All this stuff is, if you want me to expand on anything, but it's all sort of a lot of the things that you may have done in physics or calculus. But you can, in SymPy, we can do the dot product of vectors very easy. So I created those same two vectors here, A and B, take the dot product, and you get a scalar out, right? It's no longer a vector. That's one key thing. Dot products create scalars, and then you and in this case, you multiply the coefficients of each. Cross products can also be done. So cross products are the, if you have two vectors like this, and I cross A into B using the right-hand rule, it means that the new vector is going to be pointing into the board, into the screen here. And the cross is defined as this. It's the magnitude of the two vectors, and then the sign of the angle between them, and it's in this direction u, which is also always orthogonal to the two vectors that you're crossing. And we can also do that easily in SymPy to find the two vectors there. I can cross them, and it'll automatically compute the cross product of two vectors. And notice that the output of that is a vector. And so vectors have a lot of properties. We can dot them with each other, doing the cross products and such, and we've listed these here. This is mainly for you if you want to go back home, review this material some. I'm not going to spend an awful lot of time on that. I sort of expect that it's basic knowledge. But we're going to use vectors basically to locate points. So what do you think are the most important points in a moving system, like a robot or a human or any of those vehicles? The end vectors? The end could be important, right? Because you might want to know, might want to track the location of that point. But what are the positions that, if you do remember back to F equals ma in your physics class, what are the most important points for forming those equations? Anybody remember? Center of mass. So often we're going to be trying to get to the center of mass of all the bodies and things. And to do that, we're going to build up sort of chains of vectors to try to locate the points that we're interested in. And this is a demonstration of two reference frames, one A here and one B that's rotated, right? And we can define a vector on this page, R, but we can express it in both of those reference frames, right? So if I think about, well, what does R look like in this reference frame? It has a distance here and a distance here that define the coefficients of the two unit vectors to get to the same point. But if I'm sitting on this reference frame and thinking about it here, well, then I go that distance in the bx direction and this distance in the by to get to the same point. So this is a key piece that we're going to have to keep in mind, is that I can think of a single vector in space, but I can view it from different reference frames, right? And I can get to the beginning and the end of that vector from either of those reference frames. And as an example, I'll do a little, so say I have point 1, right, point 2, and point 3. And then I'm going to create sort of our main reference frame here. And I'm going to call it AX. And then I'm going to create another reference frame here that's rotated relative to A, that's defined by the two unit vectors Bx and By, right? And I'm interested in understanding where this point is in either of these reference frames potentially. So the vector from this point to this point we call R. And if I know the distance A to get to here and the distance Y to get to here already, that's fine. You've got the location of that point. But it's often the case that you can sort of simplify tracking to what point you want by using sort of intermediate frames. And these are often attached to like joints. When you have, if I have a joint in my arm and I want to know this point, and this point, I can think about a reference frame attached to my shoulder. one attached to my lower arm here, and then I could travel vectors from here to here to get to the endpoint, right, that you're interested in, right? So maybe I want a robot arm that's going to pick up something, and I need to know that point. But it might be easier to travel here, because I know these lengths, right? And the way we're going to do that is sort of build up these intermediate vectors. So I'll do, if I do a vector from here to here, and I know its length, we'll call it length 1, and then I know a vector from here to here, length, and that's of length 2. So I can go from, let's name these points, O, P1, P2. So if I'm interested in the end, which might be my hand on this robot's arm, I'm after this vector, but it depends on sort of traversing from here to here. And that vector math addition, right, I can add this vector to that vector to get this vector. So we'll call this R1 and R2 vectors. So right, R equals R1 plus R2. And that'll get us to the point of interest. And to do that, we may know these, we may know the angle that this is at. So if I call this theta 1, and I may know that the angle that this is at right here, theta 2, right? So if I know theta 2 and the length from here to here, I have the direction and the magnitude of that vector, and I can get to that point. So R1 equals the, what does it equal? What is the x distance of R1? Anybody know that offhand? Is it sine theta or cosine theta? Cosine theta. Cosine theta, right, times that ax unit vector, right? And we missed the length there, so it's L1 times cosine theta ax. Plus, and what's the other component in the y? Sine. L1 sine theta 1 a y. And then what about R2 defined in the B frame? What are the B directions? What's the bx direction of R2? Theta 2. Yeah, it's sort of bad. I'm writing sideways. B unit vector x. And then what's the rest? You on a roll? Okay. So now we have these two components. We can add these two vectors to get the total vector, right? And so this stuff gets nasty, right? All these sines and cosines, and when you have three-dimensional rotations, which we're not even going to do today, it gets even hairier. So what does software that we're going to show you, it sort of takes care of all this. We're going to create points, and we're going to map vectors, but we won't have to, it'll do all the bookkeeping for us of all this sort of nasty stuff. And keep in mind that we had R1 is defined in one reference frame, A, and R2 is defined in another reference frame, B. So when you add those, it's not as simple as adding, I can't just add that to that, right? I have to re-express either A into B or B into A to get the whole expression. Does that make sense? So that's the fundamental things that we're going to want to use here to sort of locate all the points of interest. And this notebook, like I said, you guys can read over at home a little more. But here's an example of doing what I just did on the board with SymPy. I first create two reference frames, right? A and B. And the second one, B, is created by rotating about an axis through an angle theta. And then I can define vectors in multiple reference frames, right? So this one, A, is defined in the A reference frame, and B is defined in the B reference frame. And now when I add that, notice that it has AX, AY, AZ, when I do cross products and dot products, it manages all that sort of nasty math that we have to deal with. And also, if I do a plus b, and I express that in the A frame, right, it'll automatically convert that vector for you into being expressed in one of the reference frames. So these are sort of the key concepts about how we got to think about vectors. There's reference frames that can be rotated to each other, and we can view, if we're standing in that reference frame, we're going to see the vectors in different ways. So the rotation matrices are sort of behind the scenes. They're what contains all those sines and cosines that we started writing on the board. And they're typically defined as a tensor, a 3x3 matrix. And to get to those, I can look at a, if I type DCM, the direction cosine matrix, with respect to A, so B, the reference frame B, I can sort of get out those sines and cosines that we were writing on the board. It tracks all that for us. So that talks about there. You guys hit me with questions if this is losing you at all. So we've talked about that. Another important part, right? Everything that we're talking about is motion with respect to time. So all the derivatives that we're going to be building and all the is always with respect to time, the dt. So we're going to take derivatives with respect to time of vectors, and SymPy allows us to easily do that. If I have a vector A that we've already defined above, I can do diff with respect to the C, for example. At least I thought I could. Oh yeah, I have to give it a reference frame. Which it comes first to see the frame. So if I say with respect to C, actually I don't think I defined C. And then the reference frame A. What did I do here? Oh yeah, I did define C. Right, it'll tell me what the derivative of that is. So these are all sort of the tools that allows us. And taking the derivatives, we'll be able to get velocities and accelerations, both angular velocities and angular accelerations, and then the linear velocities and the linear accelerations. And I'm going to just move through this. We'll get into it as we create the problem. Generally, two inertial properties that describe how the mass of an object is distributed in space is described by a tensor also, which is a 3x3 symmetric matrix. And we can define those in SymPy 2 by using this inertia function. If I want to see what it looks like in a matrix, I can do that too. So that's sort of a generalized inertia matrix for a rigid body. We're going to work with forces and torques. And forces are basically vectors that act on points, right? So if I'm pushing on my arm here with some actuator, then we're going to register that this force has some direction and magnitude pushing on that point. So we typically just create a point object and have a vector for that. And then finally, once we can build up all these vectors of both the forces and torques, which are the left-hand side of the equation of motion, and the linear and angular accelerations, and then the masses and inertia, we've got all the pieces to create Newton's second law and the Newton-Euler equations fundamentally. And if you remember at the beginning, I said that Newton's second law is a second-order ordinary differential equation. And eventually, we're trying to get it into some form that looks like this. We want all the derivatives on the left-hand, all the variables we're interested in, like positions on the left-hand side, as a function of all these things. So if you rearrange these top two equations, you get a differential equation. And then to find the solution, the position, for example, we would integrate from some time to some other time this mathematical equation. So those are all the pieces to the puzzle for dynamics that we're going to sort of use to build up this model in the next couple of notebooks. Does that scare you, or is that yeah? Okay. Well, I think we'll be able to make it through it, even if you don't remember all the math details. All right, Abina, you're up, buddy.
All right, so that was a lot. So I think we'll go through this step by step, and it'll make more sense if you didn't get all that. Let's open the next notebook, the Kinematics notebook, notebook 3. All right, the first step to solving this problem is to figure out the kinematic relationships between all the rigid bodies. So first we have to define each rigid body and their relationship to one another. So first thing we'll do is import these packages, the dynamic symbols, reference frame, and point package. And then this enables printing of the equations of motions. And here we'll reload that image from the problem. Are you guys seeing the image on your phone? Previous notebook. Okay. So first thing to do is define an inertial frame for a reference frame for each rigid body. So we'll start with the inertial frame. That's just the world frame here. So we'll define that inertial frame, reference frame I. And then next we have a frame for the lower leg. So as an exercise, I want you to define a frame for the upper leg and the torso. So just kind of mimic the syntax here. Define an upper leg frame, torso frame, and use the variables ut for each. Okay, so let's show the solution here in this next slide, next cell here. We have the upper frame defined as U and the torso frame defined as T. Next, we need to define the theta so we can know the angular relationships from each frame to the next frame. So we're here, we have theta 1, 2, 3 as dynamic symbols, so symbols that can change with respect to time. Now the first thing to do is to orient the lower leg frame to the inertial frame, which is the same frame that the foot is in. So here we have the lower leg frame, use this function orient, and we orient to the inertial frame along the axis, along the z-axis of the inertial frame by the angle theta. So the z-axis is coming out of the page here. This dot here represents the z-axis coming out of the page towards you. And the positive direction theta is counterclockwise. Oh, I keep using the wrong enter here. Make sure you're hitting Control Enter or Shift Enter. So now that we have the frames defined, the lower leg frame defined with respect to the inertial frame, we can actually view the direction cosine matrix with this command. So similar to what we have here, we have the cosines and the sines relating the axis of the lower leg frame to the inertial frame. And then we can go in the opposite direction and relate the inertial frame to the lower leg frame. So it's just the negative, or the transpose of this function, of this matrix. Now we'll do the same thing for the other frames. Do the upper leg to the lower leg. So similar syntax, orient leg frame dot orient to the lower leg frame along the z-axis by the angle theta 2. And we'll see here, see here we have the directional cosine matrix of the upper leg frame to the inertial frame. And you can see how this would become more and more complicated as you add more and more segments to the chain. Here we only have 2 segments, and it's becoming quite a large matrix. We can actually simplify this, though, to make it a little bit easier to look at. Just combine the thetas into the trigonometric functions. Now, as an exercise, I'd like you to do the same thing with the torso frame. Determine the relationship between the torso frame to the lower leg, to the upper leg. I'll go in more detail.
If you can, if you want, because I totally blanked on it. Just remind me that we're going to try to create a new one that stands up. That they want to see the whole diagram. It's in that number 2 notebook.
Okay. All right, so let's load the solution here. the torso frame defined relative to the upper frame along along the z-axis of the upper leg frame. And then we see we have all three betas incorporated into this matrix. Okay, I think we may have skipped one of the notebooks where we actually showed the entire figure we're trying to derive here. So if we could go back and open notebook 2, maybe it'll provide more context of what we're doing here. I'm sorry about that. So here in the second notebook, this is what we're overall trying to do. We're trying to create a model of this. We have the simplified model of a person, and we're trying to eventually make him be able to stand up. So we have this person divided into 3 segments: the torso, the upper leg, and then the lower leg. We define these as 3 separate rigid bodies, and we need to know the angular relationships between each segment. So here, we define that as theta. And to control this person, to actually make them able to stand up, we're going to have input torques at the joints, the hip joints, the knee joint, and the ankle joint. And we'll use that to enable the person to stand up and keep their balance. Okay, so let's go back to the kinematic notebook, notebook 3. Okay, so we have the 3 reference frames defined relative to each other. Now we're going to define each point on the rigid body. So first, the joints. We'll start with the ankle joint at the foot. So we'll just define that as point A. Next, we're going to define the knee joint, the knee joint. And the knee is at the top of the lower leg. And the length of the lower leg is, we'll just call lower leg for now, lower leg length with the symbol L_L. And then we have the knee. Okay, so now we know where the ankle is. We want to define the knee at a point this distance, lower leg length, L, away from the ankle. So we're going to set position of the knee joint relative to the ankle joint at this distance, lower leg L, along the Y axis of the lower leg frame. So that's the vertical axis. And then we can actually see the vector notation of that here. So the knee is length L away from the ankle, the inertial frame. And this is in the inertial frame, I believe. Actually, this is in the expressed in the lower leg frame, and we can then express it in the inertial frame with this equation. You notice how it's essentially multiplying this equation, this vector times the rotational matrix we calculated earlier. So that's why you see these sines and cosines incorporated here. In a similar fashion, we can do the same with the hip joint. Define the upper leg length, and then a point H for the hip, and then set the position relative to the knee joint. And here it is. Here's a point in the upper leg frame, and then we can express that in the inertial frame. And then finally, we're going to define the center of mass of each object, because we're going to essentially apply forces at the center of mass. This is going to be an exercise for you to determine. So, see how we define the points of the hip, knee, and ankle joints. Similarly, I want you to define the center of mass of the lower leg, upper leg, and the torso. And then after that, you need to set the positions of those center of mass locations. So create distances dl, du, dt for the location of the center of mass, and then use a function set position here away from set the position of the center of mass relative to the previous joint.
Distances are measured from the bottom up.
Yeah. So start with the center of mass of the lower leg. You'll set the distance relative to the ankle. And then for the upper leg, relative to the knee. and so on. You have gotten solutions, so let's continue on. Here we'll load the solution so you guys can see what you should have had. Here we define the lower leg length, upper leg length, and torso length with the symbols dl, du, dt. And then we define the center points with this point equation, lower leg mass center, point and LO. And then we set the position relative to the ankle. The distance is the lower length away along the y-axis of the lower frame. And then similarly, we'll do the same with the upper leg center of mass, set the position from the ankle, and the center of mass of the torso. Now we need the kinematic differential equations, so how the angles change with respect to time. We'll define that with omegas. Omegas 1, 2, 3 for the ankle, knee, and torso. We use the function dynamic symbols, so those are symbols that change with respect to time. And then we need to enforce this relationship. Omega is equal to the time derivative of the angles. And we're going to put them all in this list, kinematic differential equation list, and that's just how we need it for later on to input into our functions. So we have each omega minus each theta, the time derivative of each theta, and those are the angular velocities. Okay, now we need to determine the angular velocities of the reference frames. We know the angular positions. We need to know how they move with respect to time. And this will be an exercise for you to figure out. So, okay, so notice how we defined we set the position of the points of the center of mass. We need to set the velocities. It'll be the same syntax, so instead of set position, we use the equation set velocity. And then you need to set the velocity of one segment with respect to another segment. So start off with the velocity of the lower leg, set it with respect to the inertial frame. And as a hint, as you start typing an equation, you can use tab complete, and it'll give you a list of all. It'll autocomplete for you, so you can get a hint of equations of functions to use. So let's just start with the first one. Lower leg frame dot set, and then hit tab, and we'll see the functions available here. Set angular velocity. I'll use a question mark to see how to use this. So we'll start with the reference frame that we're setting the lower leg frame with respect to, so that's the inertial frame. And we're setting the velocity. We already defined that as omega. There we go. So now do this. The vector. Oh yeah, so omega, that is the magnitude of the velocity, but it's along the y-axis of the inertial of the lower leg frame, or the z-axis. Yeah, sorry about that. So we have the inertial frame dot z. Okay? So we have this, means the lower leg frame rotates along the z-axis of the inertial frame by the amount omega. Okay, now set the velocities for the upper leg frame and the torso frame. Show the velocity. Yes. We do lower leg. Hey, Jason, how do you display the velocity? EDO. VEO. Okay, so you want the lower leg frame with respect to, we'll do the inertial frame.
It's actually angle in angular velocity.
Angular velocity.
Here's what makes relative to the inertial frame. We're defining the level of angular velocity. Such that
Okay, let's continue on. I'll show you the solution for the other two. So here we have upper leg frame dot set angular velocity relative to the lower leg frame by the angle omega 2 along the z-axis of the inertial frame. Same with the torso frame. Okay, now we have the angular velocity of the bodies. We need to know the linear velocities of each body. And we're going to figure out the linear velocities of the center of masses, of the center of mass points. So using this theorem here, it says if we know the angular velocity of a body and the position of a point on the body, we can determine the linear velocity of that point. So if you know the position of any point on the body and the angular velocity of that body, you can figure out that point's linear velocity. So in this equation, just states that linear velocity of a point, angular velocity of that body, and the distance to that point from one point to another. So we'll start with the ankle. We know the ankle's linear velocity because we set that as 0 in the inertial frame. So from that, we're going to figure out the linear velocity of their center of mass using this function, this method, V2 point theory. So the ankle in the inertial frame and the lower leg frame. Hold on. First set the ankle's velocity as 0, and then we can determine the other ones. I didn't actually, got to run this here. not define lower leg mass center. Okay, so this is the linear velocity of the lower leg center of mass. Same for the knee and the upper leg and torso. All right, so we've just gone through and figured out the kinematic relationships of all the bodies and points in this problem. Next is the inertial notebook. Here we're going to yeah, the next two are pretty quick, so I think we can go through that and then take a break. Okay, so this next notebook, the inertia, we're going to figure out the mass and the inertial properties of the three segments. So here, first line, import the solutions for the last problem so we don't have to retype everything. And then these methods, inertia and rigid body. We'll use these symbols. We'll just define a lower leg mass, upper leg mass, and a torso mass. At some point, we'll eventually set values for these variables. Same thing with the inertias. And then we're going to use this called an inertial dyadic to store the inertial properties. This is an inertia tensor. It stores the inertia and the reference frame that you define that inertial properties in. And here's the vector representation of that. We convert that dyadic to a matrix, and we'll see, since we're only rotating these bodies along the z-axis, we only have inertia we only have this element of the matrix here. The others are 0 because we're not rotating about any other axis. Do the same for the lower leg and the upper leg. So this gets kind of repetitive. It's nice to be able to do this with software. Okay, so we have the mass properties and the inertial properties of each rigid body. Now we got to create a rigid body, define this as a rigid body for the mechanics package to actually use this rigid body package. We'll define the lower leg segment, the mass properties, the inertial properties, the reference frame. Same for the upper leg and the torso. Okay, next notebook. We have the inertial properties defined. Now we can determine the kinetics, so the forces acting on each rigid body. Again, we'll import solutions from the last notebook. First, we'll do gravity. We'll set a symbol. The force of gravity is G. And we're going to say gravity acts at the center of mass of each rigid body and simplify it. Gravity's action force onto the center of mass of each body. So for the lower leg, we have the lower leg mass times gravity times the inertial frame y, so just in the negative y direction. And then we'll have that gravitational force acting on the lower leg mass center. We're going to put that in the tuple, store that information in a tuple. I'm not sure why those two lines are there actually, but just so you know, those are the lower leg mass center, that's a point. And then we have the gravitational force vector. Same for the upper leg and the torso vector, torso. So those gravity creates a linear force action. Now we need the torques acting at the joints, the ankle torques, knee torques, and the hip torques. Defined as those dynamic symbols that can change with respect to time. Start off with the ankle torque, or the torque on the lower leg. So on the lower leg, we have the ankle torque that's acting on the lower portion of the leg, and the knee torque acting at the knee joint. We'll see from the torque creates an equal and opposite moment on the two bodies it's acting against. So here we have a positive torque from the ankle and the negative torque coming from the knee, from the upper leg. So we'll create that torque vector. We have the ankle torque. It's in the z-axis of the inertial frame here. And then we're subtracting this knee torque. That's also that's also in the z-axis of the inertial frame. And then we'll have that torque vector here, ankle torque minus the knee torque.
Aren't the centers of rotation different?
Centers of rotation?
Like torque is relative to what? Which center?
The torque is acting here at the knee joint, or at the ankle joint here, and at the knee joint.
Okay. So can you have these two torques that are acting at two different points?
Yeah, it's acting on the same rigid body. So you can sum that to like one torque on the body, simplify that as one torque on the body. Same way we kind of did here with the gravitational force. We simplified it as just one force acting at the center of mass.
There's sort of two types of torques and moments. And in this case, point is irrelevant. It's really the sort of, you have some rigid body in space, and I apply general torque in any direction. It doesn't matter what point, it's just acting on its body. Just like there's no point that the object is spinning around, right? Being a finite point. There's instantaneous center at any time, but there's no point in the object that's actually rotating around. So you move down, the points aren't.
Yeah. It's just to make a correlation to the biomechanics. So you would have forces, you would have your muscles acting at your knee joint or your hip joint, creating torques there. Okay, so we'll put that into a tuple here for later, and do the same with the upper body, or the upper leg. We have the muscles acting at the hip joint, the muscles acting at the knee joint, that both create torques. And then finally for the torso, we only have the hip joint creating torques on the torso. All right, so up until this point, we've essentially fully defined our problem. Next step here is to create the equations of motions and actually solve the system, and then try and control it. Here, I think is a good time to take a break, and we'll be back in about 10 minutes. 20-minute break? Okay, 20 minutes, 10:50.
And so if anybody has any installation problems still, or problems, you can hang here and go. give one more minute, and then we'll jump back in to dynamics. Yeah, I think we will have plenty of time. Yeah, likely. This one's a little long. Yeah, we're doing good. Cool. All right, well, let's get started. We're just waiting on one, so I'll go ahead and start. So now we're on NO6, the equations of motion. So like Avina said at the end of the last slide, we've sort of got all the pieces of the puzzle here to get the equations of motion, Newton's second law, or the Newton-Euler equations, which basically give you, the F equals ma. So just to rethink about what we did in the last notebooks here, we've got a symbolic expression that gives us the linear velocity of each mass center, right? We have three bodies, and we've defined the vector velocity of each mass center. We've also defined the angular velocity of each rigid body, right? How the orientation, the three thetas and omegas, with reference to each body. And then we've also added all the contributing or external forces. And if you were to do you can use several methods at this point to get F equals ma. We could go on and calculate the accelerations manually and sort of build up that equation like you would maybe in a dynamics course or a physics course. But it turns out there's 5, 6, 7, there might be 10 different methods that you can sort of move on from this point to get that F equals ma. And it turns out and we've implemented a couple of automated methods. One is called Keynes' method, and another one's called Lagrange's method. And you may have heard of one or the other. We're going to use the Keynes' method class here. It basically does all the bookkeeping. You can pass it in these rigid bodies that we've defined, tell it what variables were associated with that system, and then it'll do all the crunching, and then it'll spit out the equations of motion for you automatically. And you can do that by hand or by manually and keep doing your mathematics like you would on paper. But this is sort of one of the niceties. Once you get the linear velocities and the angular velocities and all these external forces, which are those joint torques and the gravity forces, then we can spit out the equations of motion fairly easily. Correct. So we're still in symbolic land here. We're using all the sort of SymPy's tools, right? All the imports have been SymPy. So everything's going to be symbolic. We're going to actually see the equations of this three-body system written out in the mathematical form that you would if you did it by pencil and paper, right?
Where would be the limit? Can you do 4 or 5?
Yeah, there are limits. We've got a little demo. There's a little demo in the PyDay code gen that you can just give it the number of links you want and create a super long pendulum. And I've only tried like 20 or 30, and I guess I got running. If you have a really high in rigid number of bodies and degrees of freedom, essentially, we can potentially tackle the problem. It depends on the problem. There's all the factors too, what kind of constraints and different stuff. But you might want to think about some other software too, right? So there's a nice package out of Stanford called SymBody, and it powers Gazebo or partially powers Gazebo. But if you guys have heard of like Bullet, the physics engine, or open dynamics engine, these kind of things. These are all numerical, and they're all numerical based. We don't even think about these symbolic equations. But they tend to handle, like, you could handle 1,000 bodies or something, right? Better than this. So doing a 1,000-body problem here is gonna not work well unless you get a big computer with big memory and things. So okay, so first we'll bring in the solutions from the last notebooks, and we're going to bring in that Keynes method class we're going to use, and the trig simplification, and just so we can maybe try to simplify these equations. So the Keynes method class, I guess I could show that here. What's going on? If you check out the doc string, it takes a fair amount of options, but at the bare minimum, you pass in these things that we've created: the kinematical differential equations, a list of the forces, a list of particles if you had any. We didn't have any particles in our, and then a list of, basically a list of the bodies, and the bodies could be particles or bodies, and we only have 3 bodies here, so we didn't work with any particles in this. So force list, body list, and then what are the coordinates, right? So we had thetas, that are the coordinates, and then the speeds, or the angular rates, which are the u's right here. They're the omegas in our problem. And basically we can call this class. So the first thing we do is we make these lists, right? There's a list of the coordinates of the system, the 3 angles, theta, a list of the speeds, omega, right? The derivatives of those angles, the symbols that we've declared as the derivatives of angles, and then we can initialize that class and create a Kane object. And this Keynes method takes, the first argument is the inertial frame, so you need to pick some sort of base reference frame that you want to get the equations in motion with respect to. So that inertial frame, which is the ground in our case, we pass that in, and then we give it the coordinates, the speeds, and then the kinematical differential equations, which we defined in the previous notebook. And just to remind you what those look like, these are expressions that are equal to 0 that just define the relationship between the velocities and the derivative of the coordinates. Oh, open a new cell? Yeah, the shortcut key there is just Control MB for below. Control MB. And there's also all these buttons at the top. And if you do help keyboard shortcuts, that'll remind you of all those different things in the notebook interface. Okay, so we've created this Kane object, and now we're going to create a list of call loads here, right? So because we had forces, the gravitational forces, and we have these joint torques that we're going to use as to control the system. So we make a list of those, and remember those are points, and this doesn't render nicely. This is maybe sort of a bug, but it's a vector, right? The force, and then the point that it acts on. And then the torques are the body, or the reference frame that it acts on, and the vector that describes that torque. So we make a list of those. So we get those 2 lists. And Keynes' method puts the equations in a particular form. It's going to give us these terms, FR and FR star, in this equation. Now this equation is basically, it is the same thing as F equals ma and torque equals I alpha, except we just move all the terms onto one side of the equation. The FR star term is the stuff on the right side, the M and the A and the I and the alpha, and the FR is the F and the T. So this holds the all the forces due to the accelerations, and this is essentially the forces due to anything external or anything that's I'm lost there. Well, anyways, that's the form that comes out. So we've initialized the object, and we can run fr, fr star equals Keynes equations and give it the loads and bodies, and it's going to spit out, right at this point, the equations of motion. And I'm gonna run trig_simp onto it. So trig_simp tries to do trigonomic simplification of these long systems, and you can see it's taking a second. So in general, unless your system's sort of small, you may or may not want to try a lot of simplification. You'll see that even after the simplification runs, and you don't have to do this in your computer if you don't want. You could just look at them before simplifying them. But it's going to do some crunching there and try to shorten these equations so maybe they're in a readable form. But for most systems that are beyond like 1 or 2 bodies, we get equations like this, right? So here's the equations of motion of that system that we just defined, okay? So for some types of systems, it could be very valuable to look at these symbolically and think about how the variables affect each other, what's going to happen. For very simple systems, you can analytically solve that differential equation and get a solution. But in general, you have equations like this, and you can see we only have 3 bodies, and it already makes it pretty nasty. But those, in fact, that's the FR plus FR star term of the equations of motion, and that's what it spits out, and we can work with that. The last thing that I've got here is that if you remember back in the first notebook, we showed you since we can't solve this analytically, we have to integrate it numerically to get the trajectories of all those angles and speeds and stuff throughout time. And if you look up any numerical integration routine, they always want the equations in first order form, right? The derivative of the states is what they say is some function of the states in time. Well, right now we have second order ordinary differential equations that popped out right here. And I'm sorry, we have first order because we've already defined the kinematical, differential equations. And getting it into this form, the x dots are our accelerations. They're the derivatives of, if we look in that long expression, we'll find some omega dots in here, right? This right here. That's the acceleration, right? That's the angular acceleration of the third angle. And those are in each equation. So we'll see omega 2 dot, and omega 3 dot in each one. And so if we want to get all those omega dots on the left-hand side and the rest of the stuff on the right-hand side in this form, you basically have to find the coefficients and do a matrix inversion to get it in there. So you saw those omega dots. Well, the coefficients are what I've got here is m, and that's typically called the mass matrix. They're all the coefficients to the accelerations, the proportional pieces of the accelerations due to for the forces with respect to the mass terms and stuff. So doing this to get G, which we're interested in for the numerical integration routine, we would have to invert M, right, to solve that. And that's symbolically, it's doable, but you end up with really much more giant, nasty equations of motion. So typically, we take M and we take F, which are easy to get. That requires no matrix inversion. And then we're going to when we get to the numerical solutions, we're going to do that inversion numerically, not symbolically. So the point of all that is that I've got a couple of more methods here that I can pull off the M, the mass matrix, and F, which is a vector equation of expressions. And so that first one there is the M matrix, right? All these are coefficients to the accelerations and anything with a dot on top of it in the equations. And then here we have the right-hand side of that equation, the little f, right? So those two pieces we're going to use in the next step, which is now we're going to jump to numerical land, and we're going to use tools like NumPy and SciPy and move away from SymPy, essentially, so that we can find the trajectory. And we generally call this in dynamics world simulation, right? We try to simulate the system and see how it's going to move through time. And here we're going to do a sort of a forward dynamic simulation to see what happens to the system. So now you can move into the simulate notebook, the 7th one. And we'll bring in the solutions from the previous. Now I'm going to import some things from NumPy at this point, right? Some functions that may be useful. There's a changing radians to degrees. Everything that we're going to work in is in radians, but we might want to see degrees are easy to think in. We're going to work with NumPy arrays and create arrays of zeros, and then linspace is a nice function too. We're also going to grab this SciPy ODE int function, right? An ordinary differential equation integration routine that Obina showed on the first notebook. And from PyDy, now this is where you could possibly hit a bug if we haven't got that updated yet. We're going to bring in this function that says generate ODE function, and what that does is it's going to help us go from symbolic land to a function that we can evaluate numerically. And we're also going to make some plots, right? So the sort of de facto 2D plotting library in Python is called matplotlib. What's up?
Which one was the one that goes from symbolic to numerical?
That's this function right here, generate ODE function, and I'll talk about it in more detail. Is what allows you to go from those equations of motion that we just had to numerical stuff, and it'll generate. You can generate different types of code, Python or C or different things. So, all right, I'm going to bring in matplotlib, and this is a little magic function from IPython that allows us to do inline planning. Oh yeah, Abina showed you those in the beginning, and then just set a couple other parameters. So, first thing here. We're going to need I'm going to make a list of all the constants in the problem, all right? So we had masses and lengths and the acceleration due to gravity and the inertia terms. So all those don't change with time. So we'll make a list with those. And then there's other things, the ones that change with time, the coordinates, right, and the speeds. And those are the states of our system. That's what they're typically called. And lastly, we're going to need a list called specified that contains all of the specified quantities. And the specified quantities in this case are those torques, the joint torques. So those are going to be the inputs to the system. We're going to try to find the best inputs to those torques to make this person stand up, right? So if you want to make a list of that for a short exercise, I'll give you a couple of minutes. It's not that exciting of an exercise. You're probably deep into the... So everybody got that? Remembered what the variable names are? I guess that's the hardest part of that. So if we load the solution, right, we just make a list of those. We'll call it specified. Okay, so let's talk about ODE int a little bit, right? If I look at the doc string for ODE int, what it needs is it needs a function, right, that's callable. And that function is defined such that the derivative of the arguments, it returns the derivative of the arguments with respect to t given the arguments at the current time and the value of value of time at the current time. So you have to pass in this function, and that's the x dot equals gx, gx of t that I showed a minute ago. And then it also needs initial conditions. So if you remember, when you integrate systems or you integrate equations, you always have a what's the word I want here? If you have an integral that's that doesn't have a stop in it, indefinite. That's the word I want. If you have an indefinite integral, there's always a constant at the end, and the only way to determine that constant is basically to solve the initial value problem if it's a differential equation. So here we have to provide some initial state. So that person, this model, this person we've created, he's got to be in some initial configuration when we started. So that's what that represents. And then finally, here it requires a value of time, or an array of time. So a sequence of times that you would like to know what the angles and speeds are going to be. And finally, we're going to use the args function here too. All those values that are constants, we're going to pass in through args, and we're also going to pass in anything that we want to control the system with, the values of the specified torques. So that's ODE-int, and that's typical sort of formulation that you would see in lots of packages. And this runs some algorithms from ODE-pack, in particular the LSOTA routine. So this is just the old Fortran routine, really, that's does a nice job integrating stiff and non-stiff systems. So that's available in SciPy among other kind of ODE integrators. You can see it's got a ton of other parameters too if your problem requires that or you're interested in other things. So to get that function that we pass in, we're going to use that generate ODE function call, and I'm going to give it the symbolic mass matrix, the symbolic forcing vector, the symbolic list of the constants, coordinates, speeds, and the specifieds, right? So all that on the right-hand side is symbolic stuff, and what comes out on the left is a function, a Python function that can be evaluated numerically, right? So if I pass in numerical values, it'll evaluate that. It'll return the values of the right-hand side of that ordinary differential equation. So it calculates the derivatives of the states, and the states are the coordinates and the speeds. So it's going to output the speeds and the accelerations. So we run that. It creates a function, right? We can check the type. What's up?
I'm not sure, but I guess you mentioned that you can do something with C as well with this generate.
Yeah, we've got some functionality. It's not plain. It generates C code, but I can do generator. This stuff is new too. So if you really want to get down to the dirty stuff in this, talk to me and we'll generator, if I can spell it. And we have a Python option. It generates some C code and then does a little wrapper automatically for you. So if you don't have Python installed, it won't work, and it may not work on all operating systems either. I don't know at this point. But and then we have the Theano thing that I told you about. We've been playing with that some too. So Theano basically takes sort of symbolic type of definitions in mathematics and tries to write fast code for it. And they have options for spitting out to CUDA GPUs and stuff too. So we've been exploring ways to try to get your fast code out of this. And this stuff is still somewhat experimental here, but and SymPy has a lot of code generation features in it too. So, and you can generate Fortran and C and JavaScript and different things that you'd be interested in from this. So right now we're just generating Python code actually. So the default is generates Python code, so that's as fast as it would run. But for this problem, it's plenty. And then if I look at the doc string on that function that we just created, it gives you some information, right? It's in the form that ODE wants, right? It takes the states. It outputs, given the states x, it outputs x prime, the derivatives of the states, and you have to pass in t, and then that's the current time. The states have to be in this order, right? Theta 1, theta 2, theta 3, omega 1, omega 2, omega 3. And then in the args, extra args, we're going to pass in numerical values for the constants, right? So if his leg weighs 3 kilograms, we pass in 3 kilograms, the numerical value. And then finally, the specified thing in this args dictionary can either be a value, right? So we can set all the torques to 0, or we're going to use a little later, we're going to create, you can pass in a function here, right? And this is how you might want to control the system. You can give a function it's a function of the current state. So I can say, well, how far am I falling down? Okay, well, calculate some torques that are going to bring me back up. So we're going to pass in a function eventually, but right now we'll just do zeros. Okay, so we've got that function. Now we want to simulate it. The first thing is we want to create some initial conditions. So I'm going to start by creating an array of zeros, right? And if you just want to see that, right? This creates a NumPy array of zeros. But then I'm going to go ahead and if I start him off with everything at 0, he'll be standing up. And if in an ideal world, well, he'll stand there forever. So we want to see some motion. So I'm going to set the the first 3 values, which are the angles, to 2 degrees. So we're going to start him off. Each one of those angles are going to be set 2 degrees. And then here, I need some numerical values for all of those, like the leg lengths, the masses, the inertia terms. And you can get these from literature and stuff. A lot of people have measured them. We have another little package here that tries to estimate them for you. So that's where I got those numbers from. But these are realistic numbers for a human, essentially. Okay. So the exercise here is we're going to set all the 3 joint torques equal to 0 for the duration of the simulation. So create a value numerical specified that's a NumPy array of length 3, and each entry is equal to 0. And then we want you to create a dictionary, and you're going to have to look back at the doc string for the right-hand side function. This args part is a Python dictionary that has 2 keys, constants and specified. And you want to create that dictionary that we can pass into the function. And then finally, create a time vector using a linspace that will give us times from 0 to 10 at 60 hertz. So I'll give you a few minutes to try to create those pieces that we need to pass into the function. Anybody got it? All right, I think I'm seeing some right answers there, so we can move on. You basically want to, like we had the zeros function, you can specify all the torques to be 0. And we need to create a dictionary where we pass in those numerical values of each, the constants and the specified. And then finally, you can use the linspace function to create a time vector that goes from, I guess I told you the wrong thing, 10 seconds, but I have 5 here. Well, 10 or 5 is fine. Okay, so now you have all the arguments that you need to evaluate the right-hand side. So if I give it, for example, the initial conditions, time equals 0, and those arguments, it computes the derivatives of the equations of motion there at that time instance. So now ODInt has something that it can work with, right? So to use ODInt, we just pass in that function. We give it the initial conditions. We give it the time vector here, right? The list of times we want the results at. And then we have to pass in args. And the notation's a little funny there because it wants a tuple. So we make sure that because we only have one argument, we make sure we pass in a tuple by adding the parentheses and the comma. And when we click that, it evaluates the equations of motion, it simulates the system, and it gives us y. And y is the output. It's the trajectories of both the coordinates, all the angles, and the speeds, the angular rate of each thing. And it gave us, so the 6 values, right? 3 angles and 3 omegas at 300 time points. So now you may want to find out what that looks like. So I call I've got the matplotlib plot command here. So if I give it t, and I'm going to use radian to degrees, so we can look at these in degrees instead of radians. A little easier to think about what's going on. And I'm going to plot all of the time points. But in the first one, I'm just going to plot the first 3, right? And those are the angles: theta 1, theta 2, and theta 3. Put some labels and add a legend. And here I can pass in, I'm using the vlatex command here to convert the SymPy symbols into LaTeX for me, so it'll automatically do that. And if we plot that, we get the trajectories of the 3 angles through time as we've simulated it, given those initial conditions. So what do you guys think? What's going on with this system? Unstable? And why do you think that? Yeah. So it's, right, 360 degrees is one rotation. So we're flipping around like crazy here. So that's sort of to be expected. We've sort of got it's well-known theory that sort of what we've designed here, that multi-link pendulums are chaotic systems. And if we don't have any, like our body, if we didn't have muscles that are keeping us up, well, we'd be flipping around like that too. So go ahead and make a plot of the speeds for your exercise there. Let's see what the last 3 variables in that y array look like. Let's see if that tells us any more. Is anybody seeing what the speeds look like yet?
For why we have like 1, 2, 3, 4, 5, 6 columns,
6 columns.
and then which one is the speed?
The first 3 are the angles, and the last 3 are the speeds.
Okay.
Has anybody got the plot yet? Oh yeah, I'm seeing at least 1, 2. So the people that see the plot, what does that tell you? Anything else? Yeah, more chaos basically. So if we load the solution, I'll plot it up here. So these are the angular rates of each of the joints, omega 1, 2, and 3. And we can see that they also are going quite crazy, and rapid changes in speeds and stuff. So we have, it's really the derivative of the previous plot. So at this point, we're able to actually simulate the system, and we can make some 2D visualizations of what's going on with the plotting library. And the next notebook, Tarun is going to help us visualize this thing in 3D, so we can sort of see what's happening instead of just looking at the plots, these trajectories over time.
So I'll go. I'll just gonna start with the visualization notebook. That is 8 notebook. So now we have the data points, and we have seen how matplotlib graphs look like for those data points. Now I'm going to visualize it in 3D using the PyDiviz module. So now I'm going to again show the main figure for reference. To that, I'm just gonna import the previous notebooks. Yeah. So now I'm going to PyDiviz has some a module for defining the shapes which we are going to use for the visualizations. So we can basically use some predefined shapes which we can use for our visualization. Now, for example, I'm importing this cylinder and sphere, and also, like I'll just show you the. So yeah, these are all the shapes available for us, which we can use for our visualizations. Now I'm going to import some other methods, which we will require for our visualization, and I'll explain them when they come around during the notebook. So now, first of all, we need to create some shapes which are associated with our rigid bodies, with our links, body links. So here is a help command on sphere shape. So you can just view it. It creates a. Yeah. So I just imported PyDiviz module, and after that it contains the submodule shapes. So I just means. it gives all the classes present in that module in the form of a list. So these are the like shapes available. Yeah. Yeah. Okay. So okay, now sphere. Yeah. So we are going to create 4 spheres for different like body parts. We have an ankle, and then knee, hip, and head shape. So we are color them all black, and as you can see in this help, we can like give different colors. Default color is gray, and then we can give a name string to that shape and all radius and everything. Like it depends on which shape we are going to use. For example, for cylinder, we'll require a like length and a radius and so on. Okay. Now we are going to define a visualization frame for a visualization frame. Now, what is a visualization frame? Basically, connects a shape to a reference frame and a point. So, like for example, we have this. This is a shape, so it can be anywhere in space. Once we have attached, we attach like a point and a reference frame to this shape. Now, that is encapsulated in a visualization frame. So, like basically, we give arguments of in the visualization frame class. We give argument of like inertial frame, ankle point, and ankle shape. So it connects ankle shape to these two, this inertial frame and ankle point. So it helps to like when we are doing visualizations, it will help to move that shape in that frame and that point using that.
And the second argument, the ankle is a point or is a
It's a point. Yeah. Okay. I don't know. Ankle shape. Yeah. Sorry, I had to just execute that cell first. Yeah. Yeah. So now we are just going to create a point for a head. Means we have these 3 points, and they were used for mechanics simulations. Like we get equation of motions using these 3 points. After that, we can create other shapes apart from those to improve our visualization basically. So we are going to define a head shape, a shape for a head, sorry, and then here we're going to attach a visualization frame to that shape. Just yeah. So after that, now we need to we have got the spheres for point the particular points, and we have got a sphere for an head. Now we are going to define the links between these points using cylinders. So for those links, we have to like define these points. Like we have lower leg center, upper leg center, and then torso center. So for example, this is our say. We are going to define a center here, and then we are going to define a cylinder like this. So that and then we are going to then again attach a visualization frame, which I'll tell you a little later now. So yeah. So we are going to just set the position of these points, like lower leg center or set position. You might have already seen it in the earlier notebooks, how to set positions for different points. After that, yeah. So we have got these constants which we were using in the earlier notebooks, and the numerical constants. We are going to just simply zip it in a dictionary, so that we can use it for our visualization purposes. It is more convenient. It is more for convenience purposes. So like we have all these constants and their numerical values along with them in a dictionary. So yeah. So now we are going to create some cylinders for the links. Yeah, here, for example, lower leg shape. We have a cylinder. We can name that shape according to our convenience, and then radius and length is taken from that dictionary we just created, and we are going to color it blue according to that image. The yeah. So yeah, we are going to use this color nomenclature for the different parts, body parts. Yeah. So we are going to create this lower leg shape. We are given the shape, and then we are going to use that shape for a visualization frame. Again, we can name our visualization frames accordingly. In this visualization frame, I am giving like a name argument and 3 other arguments. One is the like reference frame for that shape, and then a point, and then the shape itself, the shape class. Similarly, we are going to create upper leg shape, and then we are going to define the upper leg visualization frame for that shape, and similarly for a torso. So I'll just now we have defined all the shapes which are required for our visualization. We have got all the visualization frames which we have attached to all the shapes. Now we are going to create a scene class. So yeah, here's a help command on scene. So basically what scene does is it's like a canvas. It takes all the it takes all the arguments, and then it creates the visualization on a canvas. So I'll just explain how it is done. Yeah. So first we are going to define a new scene with the arguments of. So we require 2 arguments. One is the reference frame, and another is the point. So in our case, we are using inertial frame as a reference frame, and then we have that ankle point as the base point. So we need to define scene with those arguments with reference to which we want to visualize our visualization. So I'm going to give these 2 arguments for it, inertial frame and ankle. After that, we have this scene object. Now we need to supply all the visualization frames which we want to visualize in that scene. So I've got ankle visualization frame, knee, hip, head viz, lower leg, upper leg, and torso. So these are all which we want to visualize. We can either add a few more, like for example, if I want to visualize some more details, for example, in our visualization. And it is not related to the mechanics. Means we can add more detail, like for example, a hand, something like that, anything like so. And we can add that in our visualization frame list, and then we will be able to display it when required. Yeah. So after that, now we have got the shapes. Now we need to provide the trajectory of those shapes, how they are going to move in the visualization. So we had calculated all the this y variable and these things we had calculated in the previous notebook. We are just going to use them in this method, generate visualization JSON. So it basically takes these arguments. The first 2 are the symbolic arguments, and the last 2 are the numerical arguments. It takes up those arguments and create a JSON object, which is then rendered using the package. So yeah. So now after this command is executed, I've got a JSON. It's not shown here, but I've got a JSON object in the background which contains a lot of the data, and it is connected to the shapes, those particular shapes. So yeah. So after that, this scene.display command, it runs a web server at by default it runs at 8000 port number. If that is taken or busy in some other application or something, so we will try to iterate through other ports until we find a free one. So yeah, I'm going to just execute this scene.display. So yeah, it's going to open a new
I think it's a little messed up due to the like resolution or something. So yeah, I'll just. So this is our I'm zooming using a middle mouse scrolling. Since we had defined very less like these sphere radiuses and all are defined very less in, so they are displayed in a small length, and now we can zoom in to view it. And after that, I'm just going to click on this play, and here we can see how that visualization, that data points, how they are rendered in a visualization. And also I must specify that it is a 3D visualization. So like we can just view it from different angles and so on. And then this interface has other options also, like we have this play looped option. We can just click on it and then stop the visualization. It will reset the visualization, and then we can play it in a loop for like how many times we want. And apart from that, we have this reset camera button, which resets the camera to the original initial initial state. And then we have this animation progress bar. It shows what is the extent of progress of the animation. And finally you can shut down this server using this shutdown button. No, actually, the server is running in the background, so it's a background job. We can either close this window, but that server would still be running. It is going to occupy that 8,000 port, like forever or so. So we have to just shut down it from here manually, and then we can shut it down. And okay, sorry. So a little exercise for this visualization, we can so we can, like as I had mentioned, we can add different shapes to the existing visualization. We don't need to do any mechanics stuff for that. So the exercise is to create a nose for this particular visualization. We can use like any shape, a sphere or a cone or something, and the nose should point in the x direction to show which side the person is facing. So you can try it out, maybe this exercise. You can just use the mouse scroll button. You have a scroll. How do you just scroll? I don't know how do you. Can you scroll it?
Right side or something.
There should be a. I don't know. Or maybe you can, if you will have an external mouse, because where is the middle mouse button or something? Maybe it's a double click or something. I'm not sure. No, it's not. Here it is. So so we can just zoom it in, and then we can see the visualization. Yeah. So we might have to define a visualization frame for that particular exercise, in which we are required to attach a nose to the visualization. You can look for the health command on different shapes to see what all arguments they might require. Sorry? Why?
He's doing two parallels in Mac, and he's been trying it in Firefox
So,
and
so
Chrome,
what's
but
oh,
usually
so
this always works with Ubuntu.
yeah, it usually does.
Maybe you
So
can-
you're not able to. Maybe you can just.
Can you try Safari? Oh no, I can't. No, it doesn't work because I'm not.
Yeah.
I'm not here.
So can you just like restart this kernel once, or can you just open a
Maybe we do
yeah.
start
Yeah.
and sync.
Run all and yeah. It's gonna take a while. Yeah. So okay.
It doesn't work.
It usually does on the,
It does
but I don't know why it is not.
because of the
It might be some.
something.
Might be some version issue or maybe something. I don't know. Because we're having the same Firefox here. I'll just check which version we are here. So I'll just. Any luck?
Oh, yeah.
Yeah. You have this both mouse clicks and then you can just.
Come to me.
Yeah. So when I scroll it upwards, you can just zoom in or and vice versa. When I do it downwards, it just okay. Yeah. Just yeah. Visualization frame. Yeah. So you have to add another. First, you have to define a shape. Okay. Okay. Yeah. So box with frame. Actually, you'll just override it. No. If you're using the same variable, you'll just override that variable. You should use some other name. Box with frame or something. Yeah. Yeah. Something. Visualization. Nice.
Some other, I'm not going to use initial frame
Because
you said we should change it. So I mean, a new frame, or I can just move it like.
Yeah. Because like we don't need to have an orientation for a cube. Like we can keep it or we can't. It's just a matter of reference frames are for orientation basically. So what do you have have to define
what
a
is
different
angle?
that's a point.
Okay, so these
You'll
are
have to define a
points.
point also actually.
So okay, I have to define a point. How exactly?
Yeah, nose or something.
Point shape,
Yeah.
and then define vertically. Define where to define the points.
I had a head point defined. You can just look it up option out of
Okay,
the.
let's see.
No.
Okay.
You don't have to. You have to create a new point.
Okay,
For
so
syntax, I just yeah, here it is down in the next cell.
okay, so
Yeah, like we have this head point. You can just like use similarly to create a nose point.
yeah, I know, but then here I need something that I'm going to create down there.
You can create it before it is defined.
Yeah, but then you here you are using.
No. I'm not
you're
using the head. I'm using head.
Okay, so something that you have created before, but here, okay, I see.
Here
Let's just
like
move it some. Okay, I got it.
yeah. Maybe
Just put it right now.
yeah, like that way.
And then I'm putting and
It's
head.
it's just going to be like overlapping in that way.
Okay.
So you might not be able to observe both of them.
So it will not work for both of them.
No, actually, yeah. Actually, here when you define, you give this head as the argument. So you already had like, should I?
Yeah, go ahead.
So like if say
Yeah, I
it is
know. I have two things
so
on the same thing.
same point.
Yeah.
So like
So I'm not going to show this one. This frame. I'm not going to show it in the list down there. Here I'm not going to show it.
yeah, you'll have to show it here. You'll have to mention it here, but you can create a new point, like
Okay, so okay, I'll go for a new point.
yeah, that should work. Yeah, pretty much a nose.
It's a cone, but it's
Yeah,
in
yeah.
the wrong way.
It's yeah.
Points inside. So
For that purpose, we'll have to have like define
negative
a
names or
reference frame which we will need to orient it like so that
I've oriented it inside the torso reference frame.
yeah, that is why it is like this will have to you will have to define a new reference frame like
Okay. Now
But-
it's centered here essentially
yeah.
in the torso.
You can give maybe a position relative to head or something like
I have here.
What is this N over there?
it's a name, huh?
I mean,
It's-
I'm creating this new point, and then I'm
But-
just copying this
But
one.
yeah, that's the name of that point. You have to
Okay, so-
change the name or something.
Exactly.
You
and
can
then here you have to give what? What did they say?
yeah
is
with relative to which point you want to set the position of nose
So I guess Tron to have the Tron.
from head or something. Maybe you
You have.
we have a particular point, so we can define the position of the new point with respect to that earlier point. Yeah, so yeah, one correct.
You got it?
Not like it's fine. We can maybe show it here or something.
Well, you can get. We have 30 more minutes. Or no, we have 20 more minutes. So we probably should, if we want to do the control, maybe.
Yeah, we can do the control.
You can give them some more time. Though. You can give 5 more minutes.
Okay. Yeah. So you're going to take the control notebook or
Yeah.
Okay.
If you want to give them 5
No.
more minutes on this, that's fine.
yeah, I'll just give 5 minutes and then he's trying actually. So
Successfully got a nose.
That's the right frame.
It's a stop.
That's close.
that is actually run in the background because we are using IPython notebooks. So, but if we are not using the IPython notebooks,
If I'm not using this, IPython,
yeah, because we are using IPython notebooks, that's why
close
we.
it.
No, don't please. So it is running in the background right now. So
Okay.
you can't see the requests. But what if when we are running from the script,
Mhm.
from the notepad or something, from like code writer, like if here I write all the code, the same code, then I execute from a command line
Mhm.
terminal. So then we can see all the requests. Like
Okay.
so, yeah.
So, are you going to discuss um, what problems people have used this for, or is it have people use this for real world?
Yeah, we've been using. We have means we have used on some of like we have these PyDA examples. So there are some benchmark problems. We have not been able to do all of them, or means we are right now like working on them, creating some more examples like this.
Okay.
So we have some 10 or 12 like benchmark problems in PyDA examples repository. So we're going to port all of them so that they will have this visualization.
Okay.
Yeah.
That's good.
I need to position the nose on the head.
Yeah. You can. Yeah. You can set position.
So I need to, but I don't know how I can choose the.
Like yeah, we have to give this vector length into like direction.
It's not in the right direction. I can do it in the right direction.
Okay.
This modifier doesn't generate when there's a modifier like this. If you want to do only view, that will generate a new
Okay.
modification.
Okay. So it's fine.
You see, I add this box shape key.
Yeah.
I gave it the correct parameters. Then I needed to make a frame for it. I did
First
make
you had to
frame.
get a point.
A point like a Z,
Yeah.
and they set the position of the points
With respect to hip.
hip.
So like it should
Do
be
you have another position? I don't remember.
head. Maybe you can use a head.
Head,
Yeah, because
and then the length,
yeah, it's fine.
the same thing.
Yeah, you can means it depends on what
Yeah,
what
I
you
can
want to
actually
visualize.
enter my parameters. It's not important. I just want it to work.
Yeah, yeah.
So here we have the
Box shape.
visualization frame.
It should work now.
It should work. And then now I have to. I have the center.
No.
I don't need the center.
No.
So, and then
Now
here
you
I
have a
don't need.
visualization frame. You can just simply like this. You have this visualization frame. You can simply pass it to the that.
Okay, so I can. So I don't need box shape center set position
Yeah.
because
No.
I don't need it.
Yeah.
And then here I don't.
No, you don't have to.
And here the cylinder.
You don't need anything apart from that. I think that should. That
why,
is.
why cylinder needs that one? Why here I need this one?
Yeah, it's for those links.
Okay, they're related to each other.
Yeah. Yeah.
I just basically have to
You have to,
which one?
you have to take this viz frame and add it to that list.
The list down there.
That yeah here.
Control V.
Yeah, just you have to compile it all and like.
Ready?
Yeah, I think that.
Let me go down on top. Okay, syntax error.
It's a help command, so I don't think it will just. So you have to just give the. So he created a cube nose and it.
Oh, covered the whole body.
Yeah, that's one big nose. You have to just modify that argument. One is also two because relative to point ones.
So, I don't know. Now, understand.
0.05 or something. Yeah, that looks good. It's a nice nose. It's a cone or some. What is it? Is it a cylinder?
It's a cone.
Oh, okay. Yeah, that's a nice nose.
You want to show that? We need somebody to show something.
Yeah, we can have this. We can have a look at this one.
You got one?
It's a real
He's
looking
got
nose.
He's got nose. Come over here, my friend.
No battery.
Huh? Oh, no battery. Oh, you'll die as soon as you unplug? Okay. All right. Well, if you guys want to see what's your name, Oscar has a nose in the front of his. On his computer. Anybody else close? You got fingers?
Sorry.
Be off the battery here.
If I wanted to just change it to a nose.
Yeah, actually,
steps, right?
yeah, you just
Is
gave
it-
that
is
torso
yeah,
length.
torso length.
So
Okay, I see.
you have to just adjust it. Yeah. You can giving it like radius of the head, this length to be the so that it just.
Maybe find the thing that I'm going to adjust.
Adam's going to show us his creation.
Or just. Yeah. Hold the.
Oh, there it is.
Yeah. You have to probably orient it. Like.
Yeah, I refreshed. I didn't.
You're not still getting. Yeah. Now. You can just play it and have a. Yeah, actually you're using inertial frame probably when defining the visual. Can you just, yeah. Where is it? No, where is the nose this frame defined?
Right here.
So, yeah, this torso frame instead of that, you'll have to create a new frame. So, yeah.
Okay. So now you guys got some idea about how to visualize this. We've got 10 minutes left, and this notebook probably takes longer than 10 minutes, and there's a lot of content. So I'm going to probably fly through it to some degree, but what this notebook is about is we have these torques that we can apply at the joints. And in real life, if we have a human or a humanoid robot or something, you could think about generating these torques with motors or our muscles in our legs that would effectively make us stand up. So we're going to try to come up with a little control algorithm using tools that are available in SciPy and NumPy to make this guy stand up. So as before, we import stuff from the previous notebooks, and we'll just skip through that. It's basically all the same. So I'm going to give a brief overview. So it's in the controls world, controlling linear systems is by far easier than controlling nonlinear systems. So what we've been working with so far is a nonlinear system. Those equations in motion, they have cosines of all the variables in it, sines of all the variables. They have powers of 2 and 4. So there are all these nonlinear terms in there. And it's possible to design controllers for nonlinear systems, but a typical approach is to try to think about what configuration would you like to linearize about, or what configuration would you like to control about, and then you can create a linear model that that's only really valid around that position. So with this standing problem, if all the angles are 0, we're standing up, and that's sort of our equilibrium point. So that's one equilibrium point. We could balance the 3 body pieces on top of each other, and we can consider that an equilibrium point. And then we can create a linear model that's only valid, that's sort of valid around smaller angles, right? It might not be valid when I'm all the way at the floor, but it'll be valid when I'm at the top. And it turns out that a lot of times you can take these linear models, create a controller, and it'll work with the nonlinear systems for a certain range of situations. So the first thing that we're going to do is we're going to turn back to the symbolics where we had the mass matrix, if you remember, and this forcing, the right-hand side, which is like we call the forcing vector. And it turns out for this particular system, it's fairly easy to linearize. The F is a vector equation, a vector list of, it's a vector of expressions. And we can linearize that by simply taking the partial derivatives of F with respect to the states, which are the coordinates and the speeds, and the partial derivatives with respect to the inputs, which are the torques that we're applying. So we can turn this equation here into a linear equation by computing the what's called the Jacobian of F with respect to the states and the Jacobian F with respect to the specified inputs. And that's going to give a form like this, where we see an F term here, FA and a FB. Once we get that, we can invert the M matrix, and we can put the equations in this form here. The change in the x dot equals AX plus BU. And this is sort of the standard form. If you've ever seen a set of linear equations for dynamical systems, for first order ODEs, this is this sort of a standard form that you can use to develop control algorithms. So to get there, we're going to first set an equilibrium point. And that we need a vector of zeros that is 6 long for the coordinates and the speeds. That's when that specifies that the person's standing up straight in its nominal configuration. And I'll create a quick little dictionary there that maps the symbolic variable in SymPy to that equilibrium value, 0. And I think, let's see, we have like 6 minutes. I think I'm just going to go through these. We're not going to do the exercises. The next thing that I do here is just create a dictionary of the constants that maps the symbols to the numerical values. And then I use the dot Jacobian method. So the forcing vector is a SymPy matrix, and I actually can just call Jacobian on that, and it'll calculate. It'll linearize this system for us. So it calculates the partial derivatives of f with respect to the coordinates and speeds, and it gives us a matrix. And then I can also do that for the and that's symbolic. This is at the equilibrium point, and that's symbolic. And then I can plug in all the numerical values and end up with a numerical matrix FA. And I'm trying to think if we have enough time to do any of these exercises. Probably not. So the exercise was do the same thing with FB. All right, so I can calculate that, and I get a matrix also. And then I can substitute the equilibrium point into the mass matrix. And finally, substitute the numerical values. So basically, I just did a bunch of substitutions. I put the equilibrium, I calculated the Jacobian, I put the equilibrium point in, and I put the numerical values of all the masses and the links and the constants. So I end up, at this point, I can use NumPy's matrix multiplication function, dot, and I can get the A matrix that I'm looking for up here, this canonical form called state space form. I got the A matrix, and the exercise here was to get the B matrix. So that's the same situation. How to form the M? So the M we already had available, right? It was the mass matrix, symbolic mass matrix of the nonlinear equations of motion. It's just the coefficients of all of the accelerations, essentially. Yeah, sorry to rush through this, but you'll have to go back and probably read some of these. But fundamentally, I end up transforming those symbolic equations into a numerical A and B matrix that define completely the linear equations of motion about the equilibrium point, which is the person standing vertically, right? All the angles and speeds are 0. So once you have that, there's a plethora of tools available to try to create controllers for this. And of course, we don't have time to go through details of control theory, and there's lots of different methods, but I'm just going to show one particular method that turns out to sometimes be fairly easy to get a controller that makes it work. And it's based on an optimization problem that is defined by this cost function, j equals 1/2 the integral, da 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 da. And it basically says, what this cost function does, it tries to, given this system and the torques that I can apply to the system to make it stand up, it tries to minimize the error in the states with respect to the nominal position. We always want the person to be 0, so if he's away from 0, then I am going to apply some torque, some proportional torque basically, to get him back to 0. So these first two commands here, I guess I'm getting ahead of myself. There's a little function here that, number one, you got to make sure your system is controllable, and there's a neat little theorem that you can use on the A and B matrix, and that function right there implements that. And it tells me that yes, I can control this system with the given inputs. So that's sort of a test you always have to do. But this optimization problem is a pretty elegant solution, and it basically tries to minimize the error in where you want to be, and also minimize the amount of torque. So it's not going to use thousands of newton meters of torque to try to get it there as fast as it can. It's going to try to use a balance of the minimal torque we would need to get back to the right, and also a balance of not being too far off of our system. And in the Q and the R matrix in this equation are sort of the weightings. It says spend more energy in the torque so I get back faster, versus make sure I get back to the right place and spend less energy. So they're basically just weighting matrices. And you'll have to look that up on Wikipedia probably or read some of this. I've got a couple of Wikipedia links and stuff here. But this problem, the cool thing about it is that there's an algebraic solution that gives you the value, this gain matrix K, which are basically the proportionality constants that relate whatever the error in the state is to what torques we're supposed to apply. And since I'm at time right now, so I'm just going to run this. SciPy can solve that algebraic equation with you with the solve continuous ARE. We're just going to pick nominal values for the weighting matrices, and then I can calculate K. That's my gain matrix. And then I can pass in, if you remember, a function to the right-hand side. And we're going to create a controller function that will do that. And that's basically says, take that gain matrix that I have, multiply it by the error in the states away from nominal, and send back the torques that are supposed to be applied at every instant of time. Right? So I do that, and then this last exercise, once I provide that, say now I set the specified argument in my dictionary to the controller function, then I can integrate the equations of motion with this function in place. That's how I close the loop. I close the loop. And if you, yeah, I'm rushing through this, so you can talk to me afterwards if it's, but now, right, we plot the trajectory. What do we see? Stable. It doesn't go crazy. And we can, and the speeds look good. And lastly, right, I can regenerate that visualization. I can run the visualizer here, and he starts in the same initial condition. He fell down before, but now he does the right torque, stands up and balances. Okay, well, we're at the end of time. That's the deal. That allows you to try to think about the motion of systems, and from generating the equations of motion to simulation to finally a little brief bit about how you would actually control the system. So thank you all for your time today, and if you want to find out more information, PyDI is sort of our team name here, and there's some websites. A lot of this was SymPy too that goes on. That's another project that I'm involved in, and you can do a lot more with SymPy besides this. And if you have any questions about this stuff, let me know. So thank you guys. Thanks, and thanks Sabina and Tarun for helping too. Hey.